Okay, we can get started.
Okay, cool, cool. Right. So we'll start off with not actually projective geometry. We'll start off with this cool thing called the. Okay, I'll have to write a little bit bigger. Yeah, cool thing called the ratio lemma. Okay, I don't know why my writing is not neat right now. Okay, at any point if my writing is like terrible, please tell me. Okay. So yeah, okay. So the ratio lemma. So like, do people know what the ratio lemma is? The normal ratio lemma, not like some weird, the trigonometric one. Okay, 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 okay. So I'll write it down. So we have this triangle ABC, and what the ratio lemma says is like for any point D on BC, say for any point D on BC, what we have is just using sine rule on ABD and ACD, we get that BD over CD. This is BA over CA times sine of BAD by sine of CD. This is what the ratio lemma says. This is like quite well known, I assume. Yeah. Okay. Unmute people. People. If you know stuff, don't be afraid to say anything. And if you don't know stuff, still it's fine. He said without trigono. No. Okay. Phone. Okay. Never mind. Yeah. No. What's happening? One sec. One sec. Okay. I'll reduce the volume. Okay. Yeah. So this is the normal ratio lemma with trigono. With trigono. Yeah. So this is the normal ratio lemma. Does someone see how we can derive this or something?
Sine rules neat triangle, I guess.
Yes. And then we just take that AD is common and divide it.
Yeah, perfect, perfect. So we use sine rule in this triangle, and we use sine rule in this triangle, CAD and BAD, and yeah, we get BD over like BA is sine this over sine this, and CD over CA is sine this over sine this. But these triangles are like 180 minus each other, so the sine cancels out. I hope that's clear to everyone. Yeah, sine k is equal to sine 180 minus k. Cool, cool, cool. But now I'll just mention a slightly cooler ratio lemma, which some people might have heard of. So I'll take some segment BC, right? I'll take a segment BC, and for a point P on BC, I'll define. Okay, so don't be intimidated by this function thing in geometry. I'm just defining like a very simple thing. So like f of p with respect to this segment BC, I'll define f of p to be BP over CP. So like just the ratio of the lengths that P subtends on BC, right? I'll define this. And now what we get is if I make a triangle over here and I draw the circle, right? Now what the normal ratio lemma says is just like, okay, BP over CP is whatever, BAP over CAP times B over CA. But I'll extend this to the circumcircle and I'll let this point be D, right? And what I'm claiming now is that f of A times f of D is equal to f of P. So I want you guys to note first that this is like this just says that BA over CA is equal to BD. Okay, sorry, BP over CP is equal to BA over CA times BD over CD. That's all this is. There's nothing complicated about the F thing. I hope. So yeah, can anyone prove this now? This is also like very simple. It's nothing too.
We just do the ratio lemma two times, once for the upside and once for the downside, and then maybe using the properties of cyclic quadrilateral we can do it.
Yeah. Okay. Fair enough. Fair enough. So yeah. we take this triangle and we get that f of p with respect to this is like what? F of d. Do we actually need that though? Do we actually need? I guess. So like yeah, bp over cp is equal to bd over cd times sine of this angle over sine of this angle, but that's just this over this, I guess. Yeah, I mean, yeah. Okay, cool. So like yeah, this is just some sine rule things and or like length dash, right? So, but this is very powerful. This is very powerful. This thing, f of a times f of t is equal to f of p, and you guys should remember this with like okay. So you'll work with respect to this one segment BC, and for points on a circumcircle with BC and passing through any point on BC, you'll have that the multiplication of the 2 points on the circle is this like is the function of the point on BC. So I hope that's clear. So I'll take this one problem based on this. Not based on this, but like you can use this ratio lemma on it.
Uh, what is f of a?
Yeah, okay. F of p for any point p is defined to be bp over cp. So f of a is ba over ca. Like it appears here as well, but I didn't define f beforehand. Like there's nothing complicated. It's just like bp over cp for any p. This is like x. This is like x. F of x is equal to bx over cx. Does that work?
Yeah, good.
Yeah. Okay. Cool. So this is our new cool ratio lemma. And I have a problem. Okay, obviously, like ratio lemma, this ratio lemma thing is a repeated is just an application of sine rule, right? And this is just like this is also another application of sine rule, but this helps with ratio lemma and this both of these things. They help with like compactization, I guess. Yeah, so they help with the compactization of things. You can just visualize things better using this. This f thing is also just something that makes things compact. Okay, so Pascal's theorem. You've probably heard of this before, but I want you to prove this using this f of a times f of d is equal to f of p ratio lemma. So what it says is a, b, c, d, e, f are 6 points on a circle. Okay, a, b, c, d, e. Okay, wait. Let's make this a little better. A, T. I'll name the points later, but like, yeah, okay. So this, yeah, AD times BC, AD cap BC, sorry, yeah, AD cap BC and CF cap DE and okay, and AF cap BE. Okay, that's probably like I should probably name the points because it might get a little bit complicated. But like, yeah. So there's this weird figure with a lot of concurrencies or like intersections, I guess. And what I want you to prove is that these 3 points, which are the intersections, they're collinear. So I'll name the points A, D, cap, B, E. Okay, wait, bro. Why is this named like this? I don't know why it's named like this. It's not supposed to be like that. But like, okay, whatever. A, D, cap, B, C. It's fine if you name them whatever. It doesn't really matter. Just take random names for these. Yeah, okay. So AD cap BC, AE cap FC, and BE cap FD, they're collinear. I didn't notice that. Okay. I don't think F of C is defined. F of C over here. Oh, like yeah, it's fine. We'll not be dealing with like the edge cases or whatever. It's fine. Yeah. Also, important thing. I didn't mention this, but I should probably mention this. Throughout this class, we'll be working with directed segments or like directed lens. I hope everyone is familiar with directed lens. Like they appear in Menelaus's theorem. Like if you remember Menelaus's theorem, it looks like this, and you have
Whether
this.
direction matters.
Yeah, so like this over this, and this over this, and multiply to -1, which is like not possible with normal lens. It's only possible with directed lens. And in our case, directed lens is like if anything is above this above BC, then it's positive. If anything is below or on BC, then it's negative, or like whatever. Like if anything is on or above BC, then it's positive, like this ratio. And if it's below, then it's negative. Also, it's directed. Like yeah, if a point is above, yeah, okay, cool. So yeah, we won't be using directed lens for this ratio lemma thing as much. Like we'll just work very simple and very fast. We'll not delve into the configuration or whatever. But yeah, okay. So how can one go about showing this? Does someone have any ideas? I'll call these X, Y, and Z. Okay. Any ideas? Any ideas?
Extend XYZ onto the circle.
The line. Okay.
Yeah, the line.
I'll call this P and Q. Also, by the way, the thing for using the ratio lemma, the first thing you need to do is you need to define the line with respect to which you're using it, right? Because like f, obviously you have to define, like you're using b and c, you have to define that. So yeah, so first thing you need to do is you need to identify a thing you can use. What thing are you going to use? Go ahead. Any segment you can use.
You
What
can use
segment?
any segment, I think.
Can use though. I mean, like if I use AB, that's
I
like
mean, like AD or BC, preferably.
AD. Okay, AD. What you get? AD you get. Okay, use AD. You get BC is X, and then you get. But like, look, this intersection. This intersection is in the middle of nowhere, right?
Yeah.
And if you use if you use AD, then it's not really getting resolved. It's like okay, E is there and A is there, but like Y is still in the middle of nowhere. You can't do anything about it. So we want something which has all of the points X, Y, and Z on it. And the only thing possible is
PQ
obviously
only, okay.
PQ. Yeah, PQ. So we'll define f of x now to be px over. Okay, I should probably use a better name. F of point names. F of w is equal to pw over qw for all w. Right. I'll just define this. So now, what is f of x? What is f of x?
Px upon qx.
Yeah, px upon qx. Right. So now we can see that there's a lot of line segments passing through x, right? There's a lot of line segments passing through x. So we can actually calculate f of x based on other points f's using this ratio lemma. F of a times f of d is equal to f of p for a point p on pc, right? So what is f of x? Like depending on other points.
F of a into f of d
Correct, correct. Very
and
nice.
f of b into f of c.
Yeah, and f of b into f of c. Cool. Right. Yeah. Okay, cool. And now let's look at f of y. Similarly, f of y is also just like f of a times f of e, which is also equal to f of c times f of f. Is everything clear up till now? Is there anything that's not clear? Does this work?
Clear.
Okay, fine. So now I
Now we
want to.
can use,
Yeah, okay.
sorry.
Go ahead.
Now we can use a phantom point or something.
Cool. Okay, so what do you want to do?
Like define the intersection of BE and PQB to be Z dash.
Okay, okay, cool. BE cap PQ, this is equal to Z dash.
So Z dash, we can just write it down as the
Okay,
So f of Z dash is equal to f of B into f of E.
f of B into f of E. Very cool. And now, and now, yeah,
Now I
no,
guess we just prove that f of b times f of e is equal to f of times f of d by using the already existing equivalences.
yeah, BE and FC, FD, right? We want to show that these are equal. Why will we be done if they're equal? Because we know that Z dash in our case is collinear with BE and PQ, and if f of f times f of d is equal to f of z, then what we will get is, yeah, we'll be done, right? Because this z dash lies on pq, and f and d both lie on the circumcircle, and we know that the only point, it's unique by the way, it's clearly unique, because pz times zq, the ratio pz times zq cannot be achieved for any other point, right? Because if suppose z is over here, then pz over zq will be more than this z, right? So if we show that f of b times f of d is equal to f of f times f of t, we'll be done. So for that, we'll just use these equalities that we've already obtained, and it should be pretty obvious. It should be pretty clear.
Yeah, you can just multiply the first equation of f of x and the last equation of f of y, like the second one, and then the
Yeah.
other two.
Okay. Cool. Cool. So we get f of a, f of d, f of c, f of f. Lol. Okay. Cool. Cool. F of d, f of f. This is equal to f of b, f of c, f of f of c, f of b, f of c, f of a, f of e, and things cancel out, everything cancels out, happy ever after. A cancels out, C cancels out. Yeah, cool. So we get f of a, f of d, f of f is equal to f of b, f of e. I'll underline them just for clarity. F of d, f of f.
So we didn't like need the phantom point, right?
I mean, we did kind of need it, right? Because like we didn't exactly need it, but like obviously you can kind of avoid it. I don't know, but like yeah, we define a point z dash which lies on b, and then we prove that it also lies on fd. So we did kind of use it. So I hope this is clear. This was a little bit slow, I guess, but like yeah, if you
Uh,
get used to it.
I have a doubt. I don't know why are we done here. I couldn't get it.
Okay, okay, okay. I'll go a little bit slow. Okay, so right. Did you get this part? Did you get this?
Yeah,
Okay, cool. Do you get this? Did you
yeah,
understand what we did here? Yeah, we
yeah.
multiplied this equation with this equation, and we multiplied this equation with this equation, right? And then those two are equal because like these two are equal and these two are equal, right?
Yes,
So
yes.
what we get is f of d times, we get this thing, this f of b times f of e is equal to f of f times f of d.
Yeah.
Now what we realize now is that z, our point, the point that we want to lie on xy, right? That point is exactly defined by like be and fd, right? Be cap
Oh,
fd.
yeah. Their
Yeah,
intersection is unique, so it
exactly, exactly, exactly. So we define z dash to be the point such that be intersects pq, and since these two are equal, we get that fd also intersects at the same point that be intersects pq. Cool. Hope that's
Mm.
clear. That works. Okay, cool, cool, cool. So yeah, this was a little bit slow. With practice it obviously gets faster. If someone knows projective or something, like if someone knows the basics of projective, then you can try to prove this using ratio lemma. If you don't, then please focus on like what's going to happen. So yeah, butterfly theorem, you can prove this with ratio lemma as well. Very cool. Yeah, this is like ratio lemma is like very powerful, very very powerful stuff. So yeah, okay. Hmm. let's actually start with some projective geometry now. Okay, we are going a little bit slow. Not really, but like, yeah, it sounds good. Okay, so we'll first of all, the very first thing that we'll do is we'll define the plane that we'll be working in, right? So take this line, random line, right? And we'll define as it approaches infinity, we'll say that there's a point at infinity, Does that make sense? That probably doesn't make sense. But yeah, for every line, we say that it approaches some point at infinity, but these two points at infinity are not the same. Yeah. Okay. So I should probably explain this a little bit better. So, okay, this line, right? It goes up to infinity, right? And this other line, it also goes off to somewhere infinity. And suppose these two are parallel, right? So usually in Euclidean geometry, we're constrained by this, like, yeah, we have this constraint that, okay, any two lines intersect, but parallel lines don't intersect, which is like fine, but it's kind of weird, right? Like every time you encounter some random problem, you have to deal with, oh, what if these two lines are parallel? What if they don't actually intersect? So in projective geometry, the plane we'll be working in, we define a point at infinity. Okay, I'll say this very clearly. We define a point at infinity for any two parallel lines in some direction, right? So these two will intersect at point at infinity 1, let's call it. And then we take these two parallel lines, right? They will also intersect, but they will intersect at some point at infinity number 2. These 2 points at infinity are not the same. Okay, and it's not to be taken like very very literally. It's not like this direction also has a point at infinity, this direction also has a point at infinity. One direction has one point at infinity. So okay, does this make sense? I can try to put in some more sense into it if you want, but this
What
is what.
what you meant is like there can be two infinity points at two different directions, right?
Yeah. Okay, so basically what the idea is, so like these two lines, let's call these lines L1 and L2, and these two yellow lines, let's call them L3 and L4, right? L3 already intersects L1 at this point, right? Okay, wait, let me, okay. Um, yeah, okay. I'll just use this. So if anything's not clear, yeah, okay, I'll get to that. So if anything's not clear, please say if it's not clear. So yeah, these two intersect already at this point. These two already intersect at this point, and this point. So they already intersect at one point, and it's clearly visible that they are diverging, right? Like the white line and the yellow line, they're not going to intersect again, obviously. Like, okay, the point at infinity existence is also not obvious, but like, yeah. So we already have an intersection point for these like four lines. So what we are going to do for any two different directions, right? For every single direction, like I'll make a sort of origin, and I'll make several different directions, right? Direction. So for all of these different directions, I'll say that there's a point at infinity in that direction. But all of the point at infinities are not the same. These point at infinities are not the same. Not the same. But for every single parallel line, like for every single pair of parallel lines, they will intersect at the same point because they are going in the same direction, right? They are both going east, say, or like these two are both going north, or these two are both going west. Okay, not west. Okay, that's like not something we'll do. but like northwest or like northeast. They're all going, if they go in one direction, we say that they intersect at that point at infinity. So yeah, as Dibangshu is saying, for any three parallel lines, would all three intersect at the same point? Yes, exactly. So we have this line as well. It's also going in the same direction. So they will all meet at this one point at infinity. But this line will go to another point at infinity. Is this clear? Is this clear? This is very, very important. The idea might seem a bit abstract right now, but it's very important to understand. Does there exist another point at infinity if we reverse the arrows of two parallel lines? No. We'll just take one. We'll just take one point at infinity for every single pair of parallel lines. Yeah, it might seem weird, like okay, there's not a point here, but there's a point here. It doesn't make sense to really think about the direction of the point at infinity, whether it's like this way or this way, because it is at infinity, right? And like infinity is a weird concept. So yeah, this is very important. I hope this is clear to everyone. If there's any doubts, please.
Couldn't understand why you didn't consider the west side if you
What?
considered the.
What?
I couldn't get why you didn't consider the west side if you considered the east.
Okay, it's just this is just like convention, I guess. Like I'm not considering the east side or the west side. Like any direction is fine. Like, but there's only one point at infinity. There's not two points at infinity. Right, okay,
Okay.
I'll
That
actually draw a perspective diagram. So like, if anyone has done drawing before, then if
I
you draw
I
something
have
like this,
seen
yeah.
I have seen that in some questions they say all the lines, points and infinity are collinear.
Yeah, I'll get to that. I'll get to that. So like, if you've done drawing before, you might you might know this concept of perspective, right? So like, if you're drawing parallel lines, right, and if you draw something like this, right, and there's like enough perspective, like there's trees over here, but there's like bigger trees over here, right? So it makes sense that the distance is getting farther away, right? But the lines are all parallel. They're all parallel, right? Like they don't look parallel, but like if you go over here somewhere, then they will be parallel.
yeah, perspective because of perspective.
Yeah, this is like perspective, right? And they all appear to be meeting at this one point over here, right? They all appear to be meeting at this one point. And this is our point at infinity. This is our point at infinity that we are talking about. But if I draw in some other direction, if I draw this perspective thing in some other direction, it will end up at a different point at infinity. So this is what I mean by point at infinity. And yeah, and every 3 points at, okay. So if this point at infinity thing is clear, anyone have done drawing before? Okay, cool. Yeah. So if this point at infinity thing is clear, again, this is convention. It doesn't make much sense to visualize this. Just imagine a very, very far away point that just exists. Okay. But yeah, if this is clear, this is one thing. All the points at infinity, all like p infinity 1, p infinity 2, it doesn't make sense to number them. It doesn't make sense to number them because they aren't countable. I assume. So like all of the points at infinity, they make a line. You can't see the line. You can see every other line, right? But this line you can't see. It's just there. Let's just assume it's there. I won't go into much detail, but just remember this: all of the points at infinity, they are collinear. Okay. So just to hit this point at infinity concept home again, assume there's this point at infinity, right? And there's a point A. If I ask you to draw the line AP infinity, and let's assume it's this line, right? Let's assume it's this line, right? And I have another point B. and I ask you to draw B P infinity, what will that line be? Can anyone tell me what that line is?
Parallel to the original line to AP infinity.
Yeah, exactly, exactly. It won't be like this. It will be like this. There's a P infinity, like the same P infinity is over here. This is the same. Yeah. So it doesn't make sense for me to draw P infinity like this, but yeah, the line will be parallel to the original line. Okay, I hope that's clear to everyone. We'll start with actual projective now. I promise we'll start with actual stuff.
Sorry.
Yeah, yeah,
Are all the points of infinity on the collinear or something?
yeah, yeah. I said this. Yeah.
Okay.
All of the points at infinity, all of the different points at infinity, they're collinear.
We're just confirming that.
Yeah, cool, cool, cool. Okay, very nice. So now that was just like a side note. That was not meant to be a long tangent, but yeah, that was just a side note. We'll define a cross ratio. What is a cross ratio? Why is the ratio cross? What do you think, guys? What do you think? Okay, so we'll define the cross ratio for any 4 points A, B, C, D. We'll define the cross ratio for any 4 points, and this will be we're defining this for any four collinear points, by the way. For now, at least, we're defining this for any four collinear points. So we have a line. We have a point A, we have a point B, we have a point C, we have a point P. And our cross ratio is defined by CA over CB divided by DA over DB. Okay, okay. Wait. Let me write it a little more beautifully. AC over CB divided by AD over DB. This is what the cross ratio is. This quantity, this is the same. This is what I mean by when I say AB semicolon CD, this quantity is what I'm referring to. This is a very, very important thing. So I like you'll visualize it like this, right? AC over CB divided by AD over DB. Okay. And okay, can anyone phrase this in terms of f of AB, like from the ratio lemma thing, if you remember that still? In terms of f of AB, this is what is this? What is this?
F of C over F of D.
Yeah, yeah. This is f of C over f of D. And again, very importantly, the lengths are directed. The lengths are directed. So AC is this way, CB is this way, AD is this way, DB is this way. So can anyone tell me whether the cross ratio is positive or negative in this setup? In this setup of points A, B, C, D, is it positive or negative?
Positive,
Yeah, yeah,
because
perfect.
CB and TB and negative.
Yeah, yeah. So it's positive in this case. And basically, when C and D are like external to AB, if they're not inside AB, then it's positive. If they're both external, then it's positive. And if they're both inside, if they're both internal, if they're like this, CD, then it's also positive. The only case where it's not positive is when something is internal, C is internal, and D is external, right? Because then what happens is AC over CB, that's positive, but AD over DB, that's negative. So positive over negative becomes negative. Yeah, negative if A, B, C, D intersect. Yeah, yeah, basically. So like if none of them is, wait, no, 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 not really, not really. Like if CD is like this, then also it is positive. So yeah, not exactly when A, B, C, D intersect. Okay, cool. So I hope everybody is following this. I hope it's clear, because now we'll do some more definitions. It's going to be more definitions for a while. So okay, so one thing someone, if you think about it, what if A, B, C, and D are all on the line at infinity? Like I'll call the line at infinity the line with all of the points at infinity, like P infinity, 1, P infinity, Q infinity, all of those points at infinity. I'll call the line through them the line at infinity. So what if they are on the line at infinity? How do I define the ratio of points for points at infinity? Does that make sense? Like how will that make sense? So I don't expect anyone to have an answer to this right now because we haven't defined it, but we will define it soon. Soon. But yeah, if only one of the point is at infinity, so like if I have A, B, and like C in the middle, say, and I have a point at infinity, then I'll define the cross ratio to be like what is the cross ratio? It's f of C over f of P infinity, right? So I'll define f of P infinity to be 1. I'll define it to be 1. 1. Because
Well,
like, yeah,
I guess we could just take lines from one point to all those points at infinity and then take a line which intersects that and you take the cross ratio of those.
okay, cool, cool, cool. Yeah, okay. I'll get to that. I'll get to that. But like, yeah, that's a good idea, and that's the idea that works. But for now, like, if there's only one point at infinity, and there's 3 points on a regular line, then I'll define the cross ratio a b c p infinity. I'll define it to be, yeah, this f of c over f of p infinity, where f of p infinity is 1. Why is f of p infinity 1? Can anyone tell me why f of p infinity is 1?
Infinity upon infinity is just
Yeah, like, yeah,
Since
basically it's
AA
like,
is almost as much as they're almost roughly the same length.
yeah,
And
they're basically
also,
like, yeah,
and
okay.
also if we use the ratio lemma on the line AB, then
Mhm.
in some way we could say that P infinity and the midpoint have the same one or something.
Yeah, I'll get to that. I'll get to that. Yeah, good idea. So like, yeah, this is okay. So f of p infinity is not 1, it's like -1. But then since f of c is like, no, wait, bro, what am I doing? What am I doing? Lord. Yeah, so like this is -1, and this is like f of c is positive because it's like ac over cb in the same direction. So yeah, it becomes like just f of c, but more like minus f of c. So the cross ratio, this cross ratio, is minus AC over CB, right? So now also, so let's think about this. Let's think about this one thing. If we have A and B, right? If we have AB, and we want to think about when AB, yeah, like I want to think about when f of P on AB is equal to f of Q. When does this happen? Where P and Q are both on AB. Does this ever happen for distinct P and Q? Does this ever happen? Why is it negative? I guess f of p infinity is equal to -1, 2. Yeah, it's a p infinity over p infinity b, right? It's a d over db. It's a p infinity over p infinity b. Like the direction is like the opposite. So yeah, that's why it's negative. I hope that question was meant for this. Yeah.
this happens if there are points at a finite distance. I don't know about infinity, but if they are at a finite distance, then that can't be true.
F of p is equal to f of q.
Yeah.
Yeah, exactly. It
External
can. Yeah. There's someone saying something.
external division of the lines or segment or something.
No, 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 no. Like
Okay.
f of p is equal to f of q can never hold for distinct points p and q. F of p is equal to f of p, f of q is equal to f of q, f of p is never equal to f of q for 2 points on the line, obviously. Like if you try to imagine a point internally and a point externally, right? PQ, then it will always be something like negative. Like it will always
Yeah,
be
it'll
f
be
of,
negative. Yeah.
yeah, because one is external, one is internal. Obviously, that does not make sense to be equal. Okay, cool. So I hope that's clear. There's this thing called uniqueness. This means uniqueness, right? Like because f of p can never equal f of q. So yeah, the cross ratio can never be 1, right? A, B, C, D, this cross ratio can never be 1. It can never be 1 because, like, if it were to be 1, it would have to be A, B, C, C, right?
Yeah.
Right? Yeah, exactly. So it can never actually be 1. And this is the way it's defined for one of the points at the point at infinity. So now what I'll do is, okay. let's think about this. Let's think about this. There's a point P. I'll zoom in. There's a point P, and there's four lines. Four lines. And I have this intersection, and I have this intersection with these. Are there four lines? One, two, three, four. Okay, I can't count, guys. I can't count. Okay, yeah. B, A, B, C, D, A dash, B dash, C dash, D dash. Now, if I ask you, I claim this, okay? Claim, claim. I don't know why I'm saying it like that. Claim A, B, C, D, the cross ratio A, B, C, D. This is equal to the cross ratio A dash, A dash, B dash, C dash, D dash. Can someone prove this? What I've done is I've taken this point P, right, and these four lines pass through them, and there's this one line L which intersects it at A, B, C, D, and there's this another line. These two aren't parallel, by the way. These two are just random lines, and I have A dash, B dash, C dash, D dash, and I want to prove that A, B, C, D is somehow miraculously equal to A dash, B dash, C dash, D dash. Can someone prove
So
this?
P is not at infinity, right?
No, no, P is not at. If P was at infinity, then like this would be parallel lines or something.
Yeah, yeah.
Yeah, P isn't at infinity. Like we'll just deal with finite cases and assume that they work for infinite cases also. Okay, so yeah, in the chat there's people saying sine law. Okay, so yeah, sine law works. Sine law definitely works, and that is what we'll be using. It just works. I just assume that it works. Okay, so like if someone wants to prove it, they can prove it. Does someone want to actually prove it, or should we just assume that it actually works? Okay, I'll assume. Yeah, I'll assume we don't actually want to length past that much. But yeah, basically what happens is these two are actually equal. A, B, C, D is actually equal to A dash, B dash, C dash, D dash. And can someone tell me why this is so like so very important? Why this is like a huge claim?
We can take a perspective at P and move the cross ratios about.
Yeah, I haven't defined what a perspective exactly is yet. But yeah, basically the thing is that no matter what this line is, right? No matter what this line is, it can be any line, and the cross ratio of the intersections will always be the same. So that means that there is an inherent property of these four lines, right? There's an inherent property of these four lines, if I call them L1, L2, L3, L4, that intersect at P, right? There's an inherent property of these four lines that that somehow magically keeps these things equal, right? And that's what I'll define to be the cross ratio of four lines which intersect at a point. So suppose L1, L2, L3, L4 meet at P, right? Then I'll define the cross ratio of four lines. Remember, we've only defined cross ratio for four points that are collinear thus far, but I'll now define cross ratio for four lines, and I'll define this to be A, B, C, D for anything. And since we know that these any ABCD that intersects the line, right, it works. Like it's always constant. So this is actually like a viable definition because any line that intersects it will work, right? Does this make sense? Does this make sense?
Yeah.
Yeah, I hope this makes sense.
Mhm.
But
Can
yeah,
we do this
basically, yeah.
for parallel lines as well? Can we do this?
Parallel lines. What? Oh, like
Yes, I
if P is
think it
if P
would.
is a point at infinity.
Yes,
Yeah,
but it would
like
have a separate proof, I guess.
yeah, I mean, like we just want to prove that these ratios are the same, but it's like, yeah, since they are parallel
Yeah.
lines, it actually probably becomes easier, right? Like because you can use
Yes.
like Thales theorem or whatever you call it, right? By laws of parallel lines, and like there's a lot of angle equalities. So yeah, it actually works out for parallel lines as well, which is very cool. It works out for everything, everything. So yeah, L1, L2, L3, L4, we define this to be ABCD for any ABCD. But now you'll be like, oh, so like every time I want to take the cross ratio of four lines, I'll have to introduce some other line, and then I'll have to take the cross ratio of the points intersecting it. So you'll be like, okay, that's very sad. I don't actually want to do that. So you realize that the inherent property of any four lines, these four lines, is the angles between them, right? Like when you do the sine rule thing, you'll end up with this being some function of those angles, these angles in between. Like if I call this theta 1, theta 2, theta 3, and stuff, this will basically end up becoming sine of something over sine of something else divided by sine of something over sine of something else. This is what it will become. And the sines are not between these angles because these are dependent on this line, right? These are dependent on this line. So you can believe this and actually derive it. Like you should probably derive this for the sake of completeness. But yeah, these angles is all that the cross ratio of any 4 points on this line depends on, and the lines ka cross ratio, that is what I'll say is this sine ratio. This is the ratio is not actually used much, so I'll not actually calculate the ratio. I'll just use this, right? L1, L2, L3, L4 is ABCD. So that's cool. That's cool. Okay, cool. Fair enough. Fair enough. Hope this is clear. Right? I've basically defined the cross ratio of four lines to be this thing where it's dependent on only the sine of the angles. Cool. Hope that's clear. If anything is not clear, please speak up because, like, obviously, me speaking up every time to ask you whether it's clear or not has to have some like efficiency losses. So yeah. Okay. So what this means is that for what this means is that if I take any 4 points A, B, C, D, right, and I take a point external to it, and then I take another line, then I can do what I'll call projection. I can project this cross ratio A, B, C, D onto this other line by simply taking the lines joining them, right, and then intersecting. And then I'll end up with points A dash, B dash, C dash, D dash, and this is the same cross ratio. This cross ratio is the same, right? Clear. Fair enough. Okay. So the last thing I'll do, I'll define the cross ratio for. Okay. Since this is getting a bit like long, the definitions and everything, and you must be getting bored, I'll do this a little bit quickly. So I'll define cross ratio for points on a circle, right? So suppose we have points A, B, C, D on a circle, right? I'll define the cross ratio of these 4 points as well. For now, we've defined the cross ratio of any four collinear points, and we've defined the cross ratio of four concurrent lines, right? Concurrent lines. This is concurrent. Yeah. So now I'll define things for points on a circle. Okay. So, okay. Hmm, hmm, hmm. Yeah. So I'll take a point P that's not ABCD. I'll not give much of motivational remarks at this point. It makes sense to do this because like we already have this projection thing and we want to keep the projection thing, which is very nice. We want to keep it like invariant. We want to make this projection property a central idea that is the core of our everything basically. So yeah, I'll take this, I'll project it, right? I'll do this. I'll take the lines through this basically, and I'll take the line through this. And so there's this line, right? This line. And suppose these intersections are like A dash, B dash, C dash, D dash, right? And what I'll say is, okay, I'll define the cross ratio for these 4 points to be the cross ratio of these 4 points on the line. Okay. And now you'll be like, okay, I know that for any line this ABCD is constant. But how do I know that for any point Q on the circle, like if I take this another Q and then I do the same thing, I do this, right? How do I know that this is constant? Like if I take this line and then I make these intersections, how do I know that the cross ratio is always constant? So yeah, how do I know this? How do I know this? How do I know this?
Given by sine law, because dpc is equals to dqc and cpb is equals to cqb.
CP, wait, what did you say? What did you say? Yeah.
By using properties of a cyclic quadrilateral, dpc is equals to dqc and cpb is equals to cqb. So if we do the sine things again, then maybe
Yeah,
the
exactly. Like there's cyclic quadrilaterals. Every angle is like almost every angle is equal. Like there's a lot of equal angles basically. So there's like like AQB and APB. So like these two angles are equal, right? Like basically these two angles are equal, these two angles are equal, and these two angles are equal, right? By cyclic quadrilaterals. So the thing that we had, this sine thing, which was dependent on the angle between the lines, right? The angles are the same, so this ratio will also inevitably be the same. So that's how we define this cross ratio for points on the circle, by taking a point and then we take the cross ratio of the lines through the point. So I hope that's clear, right? But now another surprising thing which you might not expect to have happened is that I'll erase some stuff, right? So this is how the cross ratio of 4 points on a circle is defined. The surprising thing is that this cross ratio of ABCD, right? This cross ratio is actually the same as C AC over CB divided by AD over DB, which is the same definition as four collinear points, by the way, if you remember. Like here, it's the same definition, exact same definition. So why is this? This is also because of like sine rule basically and equal angles, right? This is provable, very doable, very doable. So yeah, this cross ratio is also defined like this. Cool, cool, very cool, very cool. So yeah, that's the cross ratio segment done. We are running very low on time, and so I'll try to. Okay, so is everything clear up till now? It's very crucial that everything is clear up till now.
yeah.
Okay, very nice. Everyone.
Yeah.
Yes. Okay, okay. Very nice, very nice. Yeah. Okay. Cool. So now it's worthy to think about. You might have heard of harmonic things before, right? So what is what is this? What is this? So okay. So I'll define what harmonic things are, and then we'll see why they are so useful, so incredibly useful. So yeah, A, B. Okay, I'll actually use A, B, C, D, right? A, B, C, D is equal to -1. If ABCD is equal to -1 for any 4 points, be it they collinear, if they are concyclic, if they're collinear, if they're 4 lines even, if ABCD is -1, we define those 4 points or 4 lines to be harmonic. So now you'll be like, oh, but you already said that ABCD is being 1 is not possible, right? But yeah, that was 1. That was positive 1. That wasn't negative. If you'll recall, yeah, this is yeah, f of p is equal to f of q isn't possible by uniqueness, but -1 is possible. If one of the points is inside and one of the points is outside, what this means is basically that AC over CB is equal to AD over DB, but it's like one of them is interior, one of them is exterior. So this is like negative, right? Does this make sense?
Yeah.
Yeah. Okay, cool. But why is this so useful? Why is this so useful? So, so we'll start off with something that Pero said initially when we were doing cross ratios, and we look at AB, right? And then we look at the midpoint. We look at the midpoint. So, AB, suppose that AB mx is -1. Also, by the way, just one small note. If ABCD is -1, then ABDC is also -1. Why is this true? Why is this true? Can anyone, real quick, can anyone tell me why this is true?
Because -1 is its own inverse.
Exactly, exactly. So yeah, so like it's still AD over DB divided by AC over CB, but they are still like negatives of each other, so it's the same. And similarly, BADC is also -1. So like yeah, you can swap the orders. Like you can even do CDAB. This is also -1, right? This isn't true for all cross ratios, by the way. You can't just switch around as you like for all cross ratios. This is only true for harmonic things. Harmonic means the cross ratio is -1. Why we can do this is because 1 over -1 is equal to -1. So that's why we can do this. Okay, cool. So yeah, I want to find a point x such that ABMX is -1.
P infinity.
Yeah, exactly. That's very cool, isn't it? Like you have this midpoint, and then suddenly the point at infinity pops in. So yeah, so x has to be the point at infinity for this to hold. Why? Because like am over mb is equal to 1, and ax over xb, where x is p infinity, that is -1 for p infinity. So yeah, so a property of cross ratio, a property of harmonic things is that a b m p infinity is -1, which is cool. Let's discuss more of these properties. More of these properties. So, where else do we think they could appear? So, okay, let's think about this. Mm, this, 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 this. Okay, this is a triangle A, B, C, P, Q, and let's say they meet at R. Okay, let's say this is R. Why can't I write R? And let's say this is S, let's say this is T, whatever. And now I can you spot a harmonic bundle? So like any four collinear points that are harmonic, I'll call them a harmonic bundle from now on, instead of calling them a harmonic thing, which is like very vague. So yeah, I'll call them a harmonic bundle. Can you spot a harmonic bundle in this diagram? Here what's happening is CT, BS, and AP are concurring at a point, which is reminiscent of Seva's theorem. And yeah, and then TSQ are collinear, where yeah, TSQ are collinear, where this is like BS, CT, and yeah, Q. So this is reminiscent of Menelaus's theorem. So where can
So,
you see a harmonic bundle?
so if we have S is the intersection of TS and AR, then DXSQ is harmonic, I guess.
Yeah, okay. Why is that?
Because it's the same lines, only there's a new line intersecting them. Which also means that AXRP is harmonic.
AXRP is harmonic? No, no, no. Like, why is TSS? Why is this thing? Why is this harmonic?
Because if we draw a line from A to Q, then they're on the same lines, just intersecting with different lines. And by the same argument that we get A, X, and R, P are also harmonic.
Okay. Wait. Yeah. So you seem to have skipped a few steps. I think I couldn't understand exactly what you're saying. Like, I assume what you were saying first of all is that BCPQ is harmonic. I didn't actually state this already. So I assume you were already saying this, right? Yeah. Okay. Why is this true? Why is this true? I see people have pointed out that BCPQ is harmonic in the chat. Why is this true? Okay, I'll just state why it's true. It's because the BP over PC, this by Cheva's theorem, or like Siva's theorem, or whatever you want to call it, BP over PC is equal to like BP over PC times CS over SA times AT over TB. This is equal to this is equal to 1. And by Menelaus's theorem, PQ over QC times this same thing. This is equal to -1. So when we divide these two equations, we get BP over PC divided by BQ over QC. This is equal to -1. So yeah, this is why this is -1. And yeah, if we project stuff, so yeah, I hope the idea of projecting stuff is clear by the way, because this is the projecting idea is literally in the word projective. Basically, the projecting idea is that you can project stuff from an external point, from a line onto a line, and then you can project stuff from a point on the circle to a point on some other line, right? Because like from ABCD on the circle, you can project from P onto some other line. So you can project from a circle to a line, from a line to a line, and also from a line to a circle, because you can project from a circle to a line. I hope that's clear. So is that clear for the people new to projective?
Can you please re-explain this last point where we divided equations?
Okay, yeah, I'll explain that. But is the idea of projecting stuff clear? Like you can take an external point and you can like stretch stuff.
Yeah.
Okay. Because I think my explanation wasn't very clear. I think I didn't actually even explain it. But like, yeah, okay, that's something you can do. Okay, cool, cool. Okay, yeah. So I'll explain this. So yeah, do you get why this is -1? This is -1 by Siva's theorem because AP, BS, and TC they concur. That's why this is true.
Equals to 1, yeah.
Yeah, and this same thing, like these points mean that I've just taken this down here. This is because of Menelaus. -1 is because of Menelaus. Because BT over TA, AS over SC, and BQ over QC. And since TSQ are collinear, this is true, right?
Oh, yeah.
Yeah, so we can divide the equations. These things appear twice. So yeah, BCPQ is -1. And now we'll project again. Projecting is a very important concept. We'll project BPCQ about A onto this line. Okay.
Yeah,
We
since the
already have.
angles are same, theta 1, theta 2, theta 3 are same, so that's why it's the
Yeah,
same thing.
basically, yeah, exactly. So you don't actually need to mention the theta one, theta two, theta three thing in an exam or like in a contest because like yeah, that's what projecting means basically. So yeah, BPCQ we project from this line onto this line through this point, and what that does is it takes B to T, it takes P to X, right, where X is defined as TQ cap AP. It takes C to S, and it takes Q to Q because Q is already on both lines. So Q stays the same. So we have this point, this point, this point, and this point. They form a harmonic bundle. And similarly, you can project like a lot of times. You can do a lot of things with this. You can even project about R, right? You can even project about R, C, R, B. Wait, I'll do these lines. Yeah, okay. So instead of projecting about A, you can project about R, and what you'll get is B goes to S, C goes to T, P goes to X, and Q stays at Q because Q is already on both the lines. So yeah, you can project about any of A and R, and yeah, it is harmonic. Cool. So there's a lot of harmonic stuff going on. I actually have a diagram made, I think, for this. Yeah, very nice, very nice.
Is
Um,
AXRP harmonic or something?
Yeah, AXRP. Yeah, like if you tilt the diagram, like if you rotate it 90 degrees, then you see that if you take the reference triangle to be QTB, right? If you take it QTB, then BS, CT, and QR they concur, right? By Seva's theorem, like not by
Yeah,
Seva's theorem, just concur. And
just
then A
concur.
is the point. A is the point that is Q, right? So I'll screenshot this one nice diagram I made beforehand. I should have just taken this. Yeah. So basically, in this diagram, right? This is the same diagram. In this diagram, every four collinear points they are harmonic. Every four collinear points, because they're just like tilts of each other, or they are like projections of each other. So these 4 points are harmonic. These 4 points are harmonic. These 4 points are harmonic, I guess. Yeah, these 4 points are harmonic. Every single pair of, or like quadruplet of 4 points is harmonic over here. I hope this is clear. This is also very important. I'm discussing all of these configurations right now where you get harmonic bundles. So the first one is like you have midpoint and point at infinity. So whenever you have midpoint, think about introducing the point at infinity. Like whenever you have midpoint and parallel lines actually, because like suppose you have this parallel line, then they already meet at the point at infinity, right? So it always makes sense to think about projective in a scenario like this. And when you have this sort of scenario where you have Seva and Mengaus configuration like this, it makes sense to think about projective. And what else? What else? What else? Okay, yeah, this is also very very important. Uh, I have a circle. I have a circle, and I have 4 points that are harmonic. A, C, B. Okay. A, B, C, D, right? Suppose A, B, C, D are harmonic. Or rather, I'll do this the other way. Okay. Suppose we have, yeah, okay. Suppose I have two tangents at A and B and they intersect at a point B, right? And then I have this line and it intersects the circle at C and D, right? I want you to show that A, B, C, D right now it's harmonic. Can you show this?
I guess we could just say that it would be on the same, D is on the same place at C. So then it would be almost the same, but because they're across from A, B, then they have to have a sign difference, so it's -1.
Uh, A and B are not in the same position with respect to CD. Like I can take this line, right?
Yes, yes.
So yeah,
Yes,
like I. Mhm.
but because that line goes through CD.
Which line? PCD.
Yes, okay, I think I'm wrong, yeah.
Wait, A
Yeah,
and P are tangents, P and PB are tangents, right?
yeah. P and PB are tangents. The
So you
drawing
can
is
just
like
join AB and first define the intersection of AB and CD just to ease, make it a little easier, maybe.
okay, cool. I'll say this is X maybe, and now what? Okay, so like yeah, if ABCD is -1, then I can do something like maybe projecting at A, right? I can project from A, and obviously like tangents are fine. Like if there's a point AA, like when I project, yeah. So okay, I'll say this ABCD, right? I have this harmonic bundle ABCD, or like any cross ratio ABCD, and I want to project them from this point A. Now you'll be like, oh, but A is already in the harmonic bundle. How do I project A, right? So what we define by convention is that any point x or like actually any line y where y is on a circle w or like omega, this line is the tangent from y to omega. Like this line is a tangent by definition. Because like you can take this as a continuity argument, I guess. Like if a dash is over here, then this line is the thing. If a dash gets closer, this line is the thing. If a dash gets even closer, this line is the thing, and then eventually it becomes tangent, right? So yeah, AA is defined to be tangent. So when I take the projection from A of ABCD onto this line L, right? I can do that. I can project things from circles to lines, right? Symmetrian stuff the Virchan is saying, but like since we haven't had a config class, I won't really use Symmetrians. Even though it's like direct with Symmetrians, I'll actually prove the Symmetrian thing. So yeah, if someone does not know what the Symmetrian is, don't worry, I'll not use anything with that. Yeah, so I'll project from A. So AA goes to P, right? The tangent goes to P, and AC it stays at P. It stays at C because C is already on L. B it goes to X, right? And D stays at D. So what I get is if ABCD is harmonic, then how do I PX I think, yeah. Then PX CD is also harmonic. But how do you go about showing this? I mean, it doesn't seem any simpler, right? I mean, yeah, okay. So like, are most of you familiar with inversion?
Yeah, our last class was inversion.
Okay, cool. Yeah. Raghav, yes. Yeah. So, do you know that x is the inverse of p with respect to this circle omega?
Yes,
Yeah.
Yeah, by definition, right? By definition.
by definition.
So, yeah, what this is alternatively asking us to prove is that for any points p, so like for any point p, I draw a line. Okay, wait, no. Okay, never mind. I'm like not working right now. Yeah. So okay, this is not actually the inverse. Like CD is like just a random line.
Oh wait, the center.
Yeah, this is the circle. Yeah. Yeah, yeah, it's not the inverse actually.
The drawing
Uh,
looks like it, I thought.
yeah, exactly. So it's not the inverse. It's not the inverse. Okay, so I'll prove this. I'll not take much time because yeah, we don't have time. So what we'll do is we'll use the ratio lemma. So the ratio lemma strikes again. Color. I'll just use green. I don't know. So yeah, so I'll define with respect to CD. I'll define f right of x is equal to xc over like cx over xt or whatever, right? Or with respect to y because there's already an x. So yeah, so what do we get? We get that f of a times f of b. Actually no. Can anyone figure out what f of p is? Can anyone figure this out? What is f of p?
CP upon PD.
Yeah, cp upon pd. But in terms of some of the points that are already in the diagram, what is f of p?
PS squared.
It's PB square, yeah. Power of a point.
P squared f of p f of c. No, actually no. Like f of p is equal to cp over pd, right? This is not cp times pd, or like it's not
Uh,
pc times pd. It's cp over pd. Yeah, so it's not pb squared. But the thing is, note that p is just equal to aa cap cd, right? P is just aa cap cd. So what we can do if we go back to ratio lemma, this is the ratio lemma, right? So f of a times f of d is equal to f of p, right? And a and d are on the circle. So what I will do, if you just move d towards a, what happens is the line becomes a tangent, and the point p is over here. This is the same thing as what we have over here, right? So basically, what I can say is by the ratio lemma, f of p is equal to f of a squared. Does this make sense? Because the intersection of PA with the circle is A.
I'm sorry, I didn't get it. Could you like just say it again?
Okay, okay. So like, do you understand why I can say that the line that is the tangent, I can say that that line is AA.
Yeah, by definition, you said it.
Yeah, like I just
And by
move it.
continuity, whatever.
Yeah, I just move it closer and closer, and it's AA, right? And what the ratio lemma says is like, suppose I have two distinct points, like this is like y and this is z. I know that f of y times f of z is equal to f of p by ratio lemma, right?
Yes. Okay.
Yeah. And so now when y and z get closer together, it becomes
Okay,
the
it just
tangent.
becomes A. AA.
Yeah, exactly. It becomes AA. So it's f of a times f of a, which is f of a squared,
Okay,
right?
okay. That's it. Okay, done.
So great question, good question. You're so like everything is clear, I hope, up till now. So since this is f of a squared, this is also f of b squared because p is the intersection of the tangents, right? This and this, right? But now, can anyone finish? Can anyone finish?
F of P is F of C into F of D. Have I made a mistake?
No, 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 no. Like this is
Okay,
f
F
of
you
of
tell
A,
us.
F of A is equal to minus F of
By
B, and so is proof.
exactly. Yes, exactly, exactly. So yeah, so like f of a squared is equal to f of b squared. Since f of a cannot equal f of b, right? F of a cannot equal f of b because otherwise they would be the same parts. Like we have defined anything under to be negative, if you remember. Anything under is negative and anything above is positive, and like things on the line are positive or whatever, right? So f of a is not equal to f of b. So f of a must be equal to minus f of b since f of a is equal to f of b squared. So what we get is AC, actually CA over AD is equal to minus BA, wait, yeah, minus BA over AD. What? Bro. Okay, sorry.
CB, I think it should be.
Yeah, lol, okay. CB over, what am I doing? Yeah, BD. Yeah, okay. And this is the definition of harmonic, right? This is the definition of what harmonic means. So yeah, we are done. We are done. ABCD is harmonic, and so interestingly enough, PXCD is also harmonic, right?
Yeah,
Right?
yeah.
Yeah, by projecting at A. And now, if we go back to what we were saying about inverses, right? If we take this circle, bruh, yeah, if we take this circle and we have point A, point B, and this is O or like M, basically the midpoint, and we have a point P outside, and I draw the tangents. This is the inverse, right? This is the inverse P dash. And by this, that PXCD is equal to -1, I have that AB, or like if you want to do it this way, PP dash AB is equal to -1. Does this make sense? Does this make sense?
Yeah, it's the same
Yeah.
thing.
It's the same thing. It's the same thing. It's just a, what do you call it? Like a special case, right? So basically, what this is saying is, since there is only one point that satisfies P dash, like there's only one point P dash such that P dash comma P comma A comma B is -1. So what this means is that we have this line, we have A and we have B and we have P, right? And suppose I want to find the point X such that ABPX is -1. All I have to do is I have to take the circle with diameter AB and I have to take the inverse, and X dash will be the inverse. Sorry, X will be the inverse. And that is the point such that PP dash AB is -1. So there's all these cool properties about harmonic bundles, which are like obviously cross ratios are also very cool. Like you have all of these invariant things. You can define cross ratio with respect to line, with respect to points, with respect to like points on a circle. But yeah, harmonic things are especially cool as we can see right now. So we have this, we have this, we have this, we have this. Also, like small thing you can note from here. Can anyone prove that? Okay, I'll just write this down. MP times. Okay, wait, no. I'll take this diagram instead. Uh, yeah, okay. Let's have Q, let's have M, right? And suppose AB PQ is equal to -1. Can someone prove that if M is the midpoint of AB, then MP times MQ is equal to MA squared?
Shall I try?
Okay, go ahead, go ahead.
So first we draw a circle with diameter AB,
Cool.
and then according to what we just saw, then if we invert around this circle, then the image of point P is Q.
Right.
So now this just follows from the definition of inversion.
Yeah, the definition of inversion says that MP times MP dash, which is just Q, it is the radius of the circle squared, and the radius
Yeah.
is MA, which is equal to MB. So this is also MB squared. Cool, cool, very nice, very nice. So this is true, this is true, and this is also like a very useful property. It may seem like it doesn't come up often. We don't have time for a lot of problems. We actually don't have time for any problems. But yeah, the last important property I want to talk. Oh wait, I don't think we'll actually have time to discuss any problems. Yeah, okay. So the last thing I want to discuss. The last thing I want to discuss with respect to harmonic things only. We'll discuss more theory actually. So yeah, the last thing I want to say is this very cool property. I won't waste time on drawing a diagram. Actually, I'm like very. I'll just copy paste diagram that I have. Okay, yeah. So what I have is BCPQ is -1. Okay, BCPQ is -1, right? And I have this point A, which forms a triangle with BAC, right? And what I have is, what I want to show is, if QAP is 90, then I want to show that BAP is equal to PAC, or like the angle is bisected. Okay, I'll actually just prove one way of this. I won't take a lot of time with this. I'll just prove the simplest thing, right? So suppose AP is the angle bisector. Okay, so like basically, whenever you see right angle at one point and you see angle bisector at other point, at the same point actually. Bro, what happened? Yeah, when you see a right angle at A, say, and you see an angle bisector at A, then the first thing you should think about, whatever problem it is, first thing you should think about is harmonics. Like, is there any set of points like this which is formed? And if there is, then this set of points is harmonic. So I'll prove this, but I'll prove only one way. And that way is like, suppose this angle is bisected, and suppose the cross ratio is -1. I'll prove that this angle is 90 degrees. Okay. And this is really simple actually, because we have BP over PC by the angle bisector theorem. This is BA over AC, right? Right. Okay. And what I have is BQ over QC. This is equal to minus BA over AC, right? But the only point such that BQ over QC is equal to BA over AC is, if you'll recall from the external angle bisector theorem, Q must be the external foot of the angle bisector, right? Right? Guys, guys, I need responses.
Can you repeat, please?
Yes.
Okay, I'll repeat. Suppose angle BAC is bisected by AP, right? And suppose BCPQ is -1, right? Then what I have is BP over PC is equal to BA over AC by angle bisector theorem, right?
Yeah.
And what I want is, since this equality holds, BQ over QC is equal to minus B over AC, right? But the only point such that this holds is the foot of the external angle bisector by the external angle bisector theorem.
Why?
Oh, uh, like the the angle bisector theorem, right?
I've
Angle
not read
bisector.
it.
What?
I have not read it actually.
Oh, angle bisector theorem is basically like A, B, C.
Angle bisector theorem.
What?
External one. This one I
Yeah,
know.
yeah. Okay, yeah. So like internal ke liye jaisa, internal we have this thing, right? Internal we have BP over PC is BA over AC. Same thing we have for external. Like if this is the external one and these two angles are equal, then and this intersects at Q, say, then BQ over QC is equal to B over AC as well. That is the external angle bisector theorem.
Okay, yeah, then it holds.
Yeah, then this thing holds. And so basically this thing is the external, this thing is the internal angle bisector, and this thing becomes the external angle bisector, right? So this angle is 90 because the angle between any internal and external angle bisector has to be 90. Why is that true? Why is that true? It's because like this is
Current
x, yeah, this
by
is x by 2, this is x by 2, this is 90 minus x by 2, this is 90 minus x by 2. So yeah, this angle is 90. Cool.
So
So
this
yeah, all
is
directions of this. Yeah.
so this is just a configuration of the internal and external angle bisectors.
Exactly. So yeah, but this is true for like, yeah, basically it's a configuration of internal and external angle bisectors. But yeah, so like if you have an angle bisector and you have the 90-degree angle, then obviously it's the external angle bisector, and obviously the cross ratio is -1. So like all directions of this hold, all three conditions are interdependent on each other basically. So yeah, these are all of the harmonic configurations. I'll slightly discuss very important things. Is everyone here free for like 15 more minutes or so? Wait, what?
Sure.
When did the class start?
yes, sure.
6 hours?
Yeah, I mean, if I'm free.
Yeah.
Yeah, yeah, because I might have slightly overplanned or something. I should not have done ratio lemma at the start. I just love ratio lemma. Okay, so yeah, poles and polars. So now after astronomy today, you'll be like, I have had enough of poles. I don't want to look at poles ever again. Or maybe NSE event well, and you're like, wow, more poles and polars. Amazing. So okay, yeah. So what is a pole and polar in geometry? So in geometry, what the polar of a point is defined with respect to a circle. So a polar is a line and a pole is a point, right? A pole is a point and a polar is a line, and the polar of a point is a line and the pole of a line is a point. Okay, so that might be a bit confusing. I'll just say what happens. So suppose we have a point P and we have this is omega, and I draw the inverse. This is P dash, and this is O, and these 3 points are collinear. Zoom out. Yellow line. Okay, so this is polar and polar. So what the polar of point P is with respect to omega, you draw the inverse, which is P dash, and you take the line perpendicular to OP through P dash, which is just this line, right? And this line is also the same line, which is the one with the tangents, right? Does that make sense? This is how I define the polar. Does that make sense?
Yes.
Yeah, okay. So basically what the polar for a point outside the circle is, it's you take the tangents and you draw the lines of the tangents. That is the polar. For a point inside, you can't draw the tangents from a point inside. So basically you just take the inverse, like for P dash say, you take the inverse P and then you draw the line perpendicular through P. I hope that makes sense. Okay. And similarly, the pole of a line. So let's take this one random line, right? I the pole of this line is I drop the foot from the center. This point is say Q, and then I take the inverse of Q, this point Q dash. This is the pole of this line. So it's basically a reverse process. So like the pole of a point is the pole of polar of x is equal to x. Does this make sense?
Yeah, opposite functions, maybe like something
Yeah,
like
it's basically opposite actions. And now, what really is surprising, it's not, I mean, I am saying that it's surprising for every single thing, but what happens is if I take this one big circle, W, I don't know why I'm calling it W when it's clearly omega, but like, yeah, and I take O, and suppose I take this point P, right? I'll take P outside actually. I take this point P, and then I take the polar of P. Suppose this is the polar of P, and then I'll take a point Q that is on this polar, and I will draw the polar of this thing. And it turns out that this line, bruh, okay, yeah, it turns out that this point that is Q dash, and then I draw the polar, right? It turns out that this polar it passes through P. So basically, what I'm trying to say is draw the polar of a point P with respect to a circle, take a point on the polar, and if you draw the polar of that point, then it will pass through P as well. Does this make sense? Like, I mean, does the statement make sense? Basically, what I'm trying to say, I'll rephrase it. I'll rephrase it. I'm trying to say that a point lies on the polar of another point if that point lies on the polar of this point, right? Q lies on the polar of P if P lies on the polar of Q. Can someone prove this? Can someone prove this? Okay, I'll
We
give
know
you.
that
Yeah.
P dash, Q dash, and Q are concyclic.
Yes.
So this is just an angle in the same segment. If one is 90, the other is 90, which implies that if one is the lying on the polar, then the other also lies on the
Exactly.
polar.
Beautiful. Beautiful. So yeah, there's a circle passing through this. Why is there a circle passing through this? Because they are inverses of each other, right? OP times OP dash is equal to OQ times OQ dash. So there's a circle passing through them. Actually, it might be better to phrase it like a little bit of phantom point argument. Although it's fine without as well. I'm just doing it for the sake of it. I don't know. So like yeah, uh, suppose Q lies on it, and then Q dash is the point such that this holds. Then we can show that they are concyclic. So yeah, it happens. Everything happens. So I hope the proof is clear. Is the proof clear?
how is
Okay.
the right statement implying implied after we prove that they are concyclic?
Okay. Okay. Yeah. Okay. Sure. Okay. So yeah, let's take Q such that Q is perpendicular over here, right? And then I will take this point Q dash, and Q dash is the inverse, and I want to show that PQ dash is perpendicular to QQ dash. But then OP times OQ dash is equal to OQ times OQ dash. So there's a circle over here, right? And by concyclicity, this angle is equal to this angle. So they are both perpendicular, right?
Okay, we use P power of a point. Got it.
Yeah, this power of point by inversion. This is the definition of inversion. So
Oh,
yeah, okay. So now you're like, now it's interesting to observe that there's this sort of duality. Like I can swap poles and polars basically now, because for any point on the polar, its polar will pass through the point, original point, right? So this is like very, I'll state this very vaguely for our purposes. But basically, what you can do is for any point pole, you can swap it with its polar, I mean, like, not like, this is just like a vague concept right now, but like you can swap it with its polar, and for three concurrent lines, you can swap them with three collinear points. So like, what am I trying to say basically? I'm trying to say this. I'll copy the diagram from Pascal's theorem. Uh, yeah, this diagram. What happened? I can't screenshot. Okay, this diagram. Where are we? Yeah, we are here, right? Yeah. So what I'm trying to say is here, right? Since the polar of any line, sorry, the polar of any point and the thing, basically, yeah, you can try to show this concretely, like when it holds and why it holds. But basically, what you can do is you can swap poles with polars and you can swap concurrent lines with collinear points. So let's take a look at what I mean. Over here, you can swap A with its polar. What is a polar of a point on the circle? Can anyone suggest what that might be?
The point on like A
Tangent.
tangent from A.
Yeah, tangent. Because like if I have the center O, the inverse of A is just A. So yeah, the line perpendicular to A, OA through A is just a tangent. And I can swap B with its tangent, with this tangent. And I can swap F with this tangent, and I can swap E with this tangent. And I can similarly keep swapping them with their tangents until I end up with like a hexagon with a circle inscribed in it, right? So I have this hexagon with a circle inscribed in it. Yeah, okay, let's just assume they are like tangent. All of these are tangent. And let's hope it's a hexagon and not a pentagon. Is it? Yeah, it's a hexagon. Cool. So yeah, I'm swapping A with A's tangent, B with B's tangent, F with F's tangent, everything with its tangent. And now what happens is AE cap CF say. What does AE cap CF become? AE cap CF just becomes like, uh, what does it become? It becomes AE is like, what is AE? If this is A, this is B. Basically, what happens is it becomes this, like this. It becomes a line. It becomes the main diagonal, right? Like because it's the intersection of two lines, it becomes the line through 2 points, right? Passing through becomes, what does passing through become? Passing through basically can be swapped with like what, lying on. Like a point lying on a line can be swapped with a line passing through 2 points. So yeah, basically what
Okay,
happens is
so we inverted or what?
not exactly inversion. We are just swapping every single pole with every single polar, kind of, right?
Okay.
Like B becomes its tangent. The inverse of B is obviously just B. We are
Yeah,
swapping it with this polar, which is the line. So
yeah,
basically,
yeah.
we end up with this hexagon, and then what we get is, instead of Pascal's theorem, we get this new theorem, which says if a circle is inscribed within this hexagon, then the diagonals of that hexagon, the main diagonals, the diagonals between the opposite points, they concur at a point because these 3 points are collinear, right? These 3 points are collinear, they become lines, and then they concur at a point. So this is what I call the dual of a theorem, or the dual of a problem, or the dual of any statement in general. When I swap pole with polar, and this is actually a theorem. This is called Bryan-Cohn's theorem. But in reality, since we have like just seen what's happening right now, in reality, this is just Pascal's theorem, but in disguise. If that makes sense. Yeah, line to point.
The swapping part when we just take the intersection, like till the hexagon it was all clear, but when we take intersections it was not clear.
Okay, okay. So like, the line AD, right? The line AD, it becomes a point, right? Okay. The line XY becomes the point that is the intersection of polar, sorry, pole, what? Yeah, polar of x cap polar of y. Does this make sense? XY gets swapped with polar of x, intersection with polar of y. This is a point. This is a line,
Okay, got
right?
it.
Yeah, okay. So yeah, so like the polar, so this line AD, right? AD becomes the polar of A cap the polar of D, right? Okay, this diagram is maybe not like very good or anything, but like yeah, it just basically becomes these intersections pairwise in some order, right? It becomes these intersections, and then again, what we have is we have this line AD cap this line BC, right? And we know that the point intersection of two lines is the line going through the pole of those two lines, right? So it becomes this line, this line, this line, and they concur. This is what a polar dual means. Thanks so much. I have to leave now. Okay. Okay, cool. So I'll end soon. I'll end soon. I hope this is clear. Is this not clear to anyone? This is not like a very amazing concept, but if this is not clear to anyone, please speak up. I'll send notes to everything by the way after on. So like if you have anything you want to go through, you should go through it after on or later on. Okay. Last thing, since we don't have any time to do any problems, maybe we can host a problem solving session on Projective later on, like sometime later in the year or something. Where can we find the notes? Yeah, we'll send the notes. We'll send the notes in the announcements thing, or like the PSETs and lecture notes thing. So yeah, I'll just finish off with this very powerful theorem, very powerful theorem, Brocard's theorem. This is like amazing theorem. What is it? What is it? What is Brocard's theorem, guys? I'll tell you what Brocard's theorem is.
I think it's like C instead of K, but it works.
Yeah, I mean, some people use K, some people use C. I'm pretty sure it's like interchangeably used. But yeah, if you want to use a C, you can use a C. No one minds. If you want to use a K, you can use a K. No one really minds. But yeah, this is Brocard's theorem. We have a cyclic quadrilateral A, B, C, D. We have intersections E, F. We have the intersection of the diagonals G. And we have, most importantly, the circumcenter O. Let's actually, should we go to GeoGebra and like, okay, there's no time. Let's not actually go to GeoGebra. The Brocard's theorem, what Brocard's theorem says, it focuses on this triangle, EFG. All right. I'll remove the lines actually. It just focuses on EFG. Also, can someone tell me where we have seen this kind of configuration before in today's class?
Just
Yeah.
now, P and Q
theorem in
interchange.
a
Well, that all those harmonic conjugates one, where you put the
Exactly.
lines.
Yes.
Sievin, kind of, whatever.
Yeah. The Seva Menelaus thing, the one with the quadrilateral and every single pair of 4 points is harmonic. I'll copy paste that thing because why not? I don't know why I didn't copy paste it originally. But yeah, this is what I'm talking about. Here, what we have is BCEF is concyclic, right? So the harmonic property doesn't go away. The harmonic property doesn't go away just because it's cyclic. Like obviously, it doesn't go away. So it's still there. And what we now have is that I'll actually place O a little bit better somewhere over here. Yeah, O over here. And what we have is EFG. The triangle EFG is self-polar. Can anyone guess what self-polar would mean?
As in
It's the same.
Okay, like
the in the poles of the lines are the points, and the lines of the poles are the not the lines of the not the poles of the points are.
poles of the point, polars of the points. Okay, yeah, I kind of get what you're trying to say, and that is what it is. Basically, what this means is E's pole is FG. Sorry, E's polar is FG. F's polar is GE, and G's polar is EF. And now, why is the circumcenter there? Can anyone provide some insight as to why the circumcenter would possibly be there? Why do you think it's there? Suppose this is true. Suppose FG is the polar of E. Suppose GE is the polar of F, and suppose EF is the polar of G,
Oh,
which we haven't.
orthocenter.
Exactly. Very nice. Very nice. Amazing. So yeah. So basically, what this means is, if these are like the poles and polars of each other, what this is basically saying is that OE is perpendicular to FG, OF is perpendicular to GE, and OG is perpendicular to EF. Right? So O is the orthocenter of the triangle EFG, which is absolutely like, could you ever imagine that this random property about cyclic quadrilaterals was lying in front of your eyes the whole time, right? And maybe you saw it, maybe you proved it as well, maybe you didn't prove it. But yeah, this is like, if you just ignore the self polar terminology and you just think about it as you intersect the diagonals, you intersect the sides, and the orthocenter of the triangle formed is the circumcenter of ABCD. Like, there's no harmonic terminology, there's no pole polar anywhere. It's just a random theorem about cyclic quadrilaterals that just so happens to be true. And now we'll prove it. So obviously we'll not prove first that O is the orthocenter because it's just implied from this thing, right? So, and any direction works. We can just prove one of them. So like, suppose we are just going to prove that F and GE are the, like, GE is the polar of F. Can someone do that? Let's see. Final problem of the day. Can anyone prove that GE is the polar of F? I'll introduce the line.
By symmetry, we can show it for anyone, like G is the polar of F.
Yeah, exactly.
That
If F is the polar of GE, then E is the polar of, sorry, FG is the polar of E, then GE is the polar of F. Yeah, you can do that. So that's what I'm asking. You only have to prove one direction. Prove that GE is the polar of F. I'll be back in a minute. Think about this for a minute. I'll be back. Okay, I'm back. Maybe that wasn't a minute actually. Lol. Okay. Okay. Any thoughts? Any thoughts?
Name the intersections maybe of EG and FB and FC.
F, B, and F, C. This intersection, you mean?
Yeah.
X, Y.
And
Oh,
now
I see. Wait, 1 second, 1 second. Sorry. What, what I didn't do maybe is that I didn't specifically mention this. I actually did, I think. But like, yeah, for if this is a point P and this is the polar of P, then like all of this is like, yeah, I did mention this, right? Like if this is the polar of P, then like this and this are harmonic. I did say
Yeah,
that.
harmonic.
Yeah. Okay, cool. Yeah, so what can one do here? So yeah, you know that
Wait,
EGXY,
y lies on the polar of F, and also x lies on the polar of F.
why does Y lie on the polar of F?
Because of Seva and that harmonic thing.
Yeah, exactly. So FYCD, bro, what am I doing? Yeah, FYCD, this is -1, right? And similarly, when we like project through E or whatever, or like just Seva laws, project through E, D goes to A, Y goes to X, C goes to B, and F stays at F. So we also have Fxab is equal to -1, right?
Yeah,
So and by this, we know that any point such that this thing is there, where P is over here, and then this point is over here, and this point is over here, this point is over here, it lies on the polar, right? So what do we have? We have that X lies on the polar. So X is on polar of F. Y is on the polar of F. So what is the polar of F?
XY, so XG.
XY is the polar of F. So EG is the polar of F because XY is EG. So we are done. F is the polar of G. G is the polar of EF. Sorry, EF is the polar of G and F is the polar of GE, which is amazing. So we are done. We are done. So yeah, O is the ortho center of EFG. Very cool. I think we should end the session here. I think it's already been like, yeah, it's already like 20 minutes up, and some people have already left. So this is all of the theory you need to know for projective geometry. All of the theory you need to know, and I guess the ratio lemma part isn't actually necessary, but it's like a very useful, very powerful thing. So yeah, I guess we will close the session for today, but definitely try the. Thank you. Yeah, definitely try the problems. I'll send a PDF. I'll send a PDF. It's very nice. I mean, I made the PDF, so like it's probably not good for me to say that it's. Don't we need Desargues? Ah, yeah. I mean, Desargues theorem is also like a theorem, I guess, but like it's not. Let's not do Desargues. I'll do this one thing. I'll just say this. Like this is also very obvious, but like if we have uh, points like this, right? If we have points like this, and suppose that the cross ratio of these things is the same. Like if A, B, C, D, and A, B dash, C dash, D dash. Suppose like we are not assuming it's -1 by the way. We are just saying that it's some random cross ratio and the cross ratio is equal. Then BB dash, CC dash, and DD dash, they concur at a point P. Why is this true? This is just true because like you can project through P.
Converse.
Yeah, this is the converse of projection basically. This is the converse of projection. So it's just trivial. Some handouts for projective geometry, you can do like EGMO, you can do stuff. I'll send, I'll actually share it right now actually. Share screen, window. Oh, the recording stopped. Has the recording stopped? Okay, it's fine. I don't really.
No,
It's still there.
Oh, it's still there. Ah, great. Yeah. So this is these are some notes. Uh, these are basically exactly the theory I have covered today. Not much more, not much less. You should still go through it. Uh, bro, where am I?
So
Yeah.
wait,
So there's
there are problems also on this?
yeah. So on ratio lemma, there's like these two problems. I already covered this. You can do this problem, and there's a problem just on like this problem is not exactly like a projective geometry problem. It's just a problem on projection. Like it's a very powerful thing. This is where harmonic actually starts, and these are all the harmonic configs. These are two simple problems you can do. You can ask any doubts or any problems you have with the problems. So like, yeah, these are basic harmonic problems. This is what this thing, by the way, a point x lies on the polar of point y if and only if y lies on the polar of point x. The weird thing with the cyclicity. This is called Lahir's theorem, like Lahir's theorem, whatever you want to call it. And duality, there's a handout on duality attached, Broca's theorem, and there's a few problems at the end, which are very cool problems. My goal for today was actually to do this problem. Maybe we will do, maybe we'll do it in some other session.
Why don't you just like let us try it and then we can discuss later in some other session.
Yeah, very true, very true. You can try this. We can discuss it later in some session, and we can also discuss some more problems in some other session. Cool, cool, very nice. So yeah, this is all of the theory. This is all of the problems.
So wait, we
Thank you.
just need this theory to solve those problems, right?
Yeah, only this theory, no external theory or anything. Okay, you actually do need this one lemma for one of the problems. I was planning on discussing it if we did the problem. Uh, but yeah, you can try it without it as well. It's very insightful. All of the problems are very insightful. But yeah, thank you for joining. I'll stop recording. If you want to stay in the meet, you can stay in the meet. If you want to leave, you can leave. Uh, Pause recording or stop recording? I don't actually know what I'm supposed to do. Stop recording.